Hello and welcome back to Botronix Labs. In this module of the Intermediate Robotics course, we're going to control a NEMA 17-stepper motor using the A4988 driver and a Raspberry Pi Pico W. Here's what you'll need for this project. A DC-DC step-up converter for step motors. A 5V logic booster or regulator for the A4988's VDD. A Raspberry Pi Pico W. An A4988 stepper motor driver. A NEMA 17 stepper motor. A 7.4V battery pack. On and off switch. We'll start by understanding how stepper motors work, then look at the A4988's pinout and microstepping modes. After wiring everything up, we'll write modular MicroPython code using object-oriented programming to control the motor in different stepping resolutions. By the end of this lesson, you'll know how to drive a stepper motor in full, half, quarter, eighth, and 16th step modes, and you'll be ready to tackle more advanced robotics projects. Let's get started. Let's start by understanding how a stepper motor like the NEMA 17 works. A stepper motor is a special type of brushless DC motor that moves in precise, fixed steps. Unlike regular DC motors, which spin continuously when powered, a stepper motor rotates in small increments, or steps, each time it receives a pulse. For example, a typical NEMA 17 stepper motor has 200 steps per revolution. That means every time you send a pulse to the motor, it rotates exactly 1.8 degrees. This precise movement is what makes stepper motors perfect for applications like 3D printers, CNC machines, and robotic arms, anywhere you need accurate positioning. Inside the motor, there are multiple coils arranged in phases. By energizing these coils in a specific sequence, we can control the direction and amount of rotation. The A4988 driver takes care of this sequencing for us. We just need to send it step pulses, and it handles the rest. Another key feature is microstepping. By activating the coils with varying current levels, the driver can move the motor in even smaller increments, like half, quarter, eighth, or 16th of a full step. This allows for smoother motion and even finer control. So, to sum up, a stepper motor like the NEMA 17 gives us precise, repeatable movement, and by using a driver like the A4988, we can easily control both the speed and the position of the motor with just a few pins from our microcontroller. You might wonder, why use a stepper motor for a self-balancing robot instead of a regular DC or servo motor? The main reason is precision. Stepper motors move in exact, repeatable steps, which means you can control the position and speed of your robot with much greater accuracy. For a self-balancing robot, this is crucial. Small, precise adjustments are needed to keep the robot upright and stable. Unlike DC motors, which can be hard to control precisely without extra sensors, stepper motors don't require feedback for basic positioning. And compared to servo motors, steppers can rotate continuously and offer higher torque at low speeds, which is ideal for balancing and making quick corrections. So, by choosing a stepper motor, you get smooth, accurate, and reliable control. Exactly what you need for a self-balancing robot approach. Let's go through the wiring step by step, using our 7.4V battery pack as the main power source. First, connect the battery pack to two modules. A DC-DC step-up converter to boost 7.4V to 12V for the stepper motor. A DC-DC 5V regulator to provide a stable 5V for Pico W board and the A4988's logic. The 12V output from the step-up converter goes to VMOT and its GND to the A4988's power GND. The 5V output from the regulator goes to VDD and logic GND. Connect the Pico W's GPIO pins to the step, DIR, MS1, MS2, and MS3 pins as shown. If you don't need to control the enable pin in code, just tie it to GND to keep the driver always enabled. Finally, connect the 4 wires from the NEMA 17 stepper motor to the A4988's output terminals, making sure to match the correct coil pairs. Double-check all your connections before powering up. With this setup, you can safely run your stepper motor and driver from a single battery pack, with both 12V and 5V rails provided by the converters. Now that everything's wired up, let's talk about microstepping. The A4988 driver lets you control how many microsteps the motor takes for each full step. This is done by setting the MS1, MS2, and MS3 pins to either high or low. For example, setting all 3 low gives you full steps, while setting all 3 high gives you 16 steps. Super smooth and precise. In your code, you can define these modes as tuples, like this. By changing the values sent to the MS1, MS2, and MS3 pins, you can switch between modes on the fly. This is great for experimenting with different resolutions and seeing how they affect your robot's movement. Let's make our code modular and reusable by creating a stepper motor class. This class will handle all the low-level details, setting the stepping mode, direction, and sending step pulses. Here's a quick look at what it does. The constructor sets up all the pins. Set_stepping_mode lets you change microstepping modes easily. Set_direction lets you choose clockwise or counterclockwise rotation. Rotate_steps sends the right number of step pulses to move the motor. Rotate_degrees lets you move the motor by a specific angle, automatically calculating the number of steps needed based on the current microstepping mode. By using a class, your code stays clean and you can easily reuse it for other projects or motors. Now let's test our setup. In your main script, you can loop through all the microstepping modes and rotate the motor a full 360 degrees in each one. This helps you see the difference in smoothness and precision for each mode. For each mode, set the stepping mode, set the direction, and call rotate_degrees, 360. You'll notice that as you increase the microstepping resolution, the motor moves more smoothly and quietly, but it also takes more steps to complete a full rotation. This is a great way to understand how microstepping affects your robot's performance. That wraps up this module on stepper motor control with the A4988 and Pico W. I hope you found it helpful and that you're excited to try these techniques in your own robotics projects. If you enjoyed this video, don't forget to follow the Botronix Labs YouTube channel for more hands-on robotics tutorials and project ideas. And if you want to download the complete MicroPython code used in this lesson, check out the link in the comments section below. Thanks for watching, and I'll see you in the next module.